We're trying to find our DC out. So we're using 12.6 volts as the output of the secondary, and we're going to be peak out. We're going to take 17 volts away from that, right? We give it around 11.9 volts. And then we're going to calculate volts DC. Well, that's not quite yet. Let's add one more thing. We'll calculate V peak secondary, so that's wrong. So V peak secondary is going to be equal to what? 12.6 divided by 0.707. And V peak out, which is going to be out of the diode, is going to be equal to V peak secondary minus 0.7, because these are silicon diodes that we're using. And then my volts DC is going to be equal to V peak out, right, divided by 3.14. And this is going to be approximately. Odds are it's not going to be exact, but it's going to be close enough, right? What we got? We got this because a sine wave varies at a precise rate. So I know that RMS is actually calculated by taking an infinite number of instantaneous voltages around the sine wave, right? Square them, so that way your negatives become positive. Take the average, and then take the square root of your answer. If it's a sine wave, that always comes up to be the sine of 45 degrees, which is 0.707. So this is what meters use. Most meters use the 0.707. They don't calculate root mean squared. But if it's a sine wave, it will always come up and be 70.7% of VP. Always. So if I can calculate VRMS, so VRMS equals to VP times 0.707, then VP would be equal to VRMS divided by 0.707. We're doing the same thing that we were doing on block. All I'm saying is 0.707 RMS will always be less than VP. So that means if I multiply by a fraction, we'll come up with a smaller number. If we divide by a fraction, we will come up with a larger number, right? You understand that? And it's in your form. It should be in the formula sheet somewhere about VP equal to VRMS divided by 0.707. You know, there's somewhere. So what would VP equal to? 12.6. We're taking for granted that the transformer is giving us exactly 12.6 volts. So what would the RMS, which is 12.6, because that's what AC is given as, is RMS. So we say we have 120 volts. We don't specify RMS, so it's assumed to be what? RMS. So this meter right here measures RMS. Now this don't say it's a true RMS meter, so it probably uses 0.707, right? Understand? I'd have to look at the data. Most of the time when they say it's a true RMS meter, they will advertise it on the So what would be peak equal? Who's got this? Jalen, you got that yet? No, he's got 17.8 for VP. Huh? Guys, you got to understand when your answer is got to be wrong. If I divide by a fraction, I always come up with a number that is the one I started. So what we're doing is the formula we calculate. I'm giving you RMS, 12.6. So if I say 12.6 what is that? Peak to peak, or is it RMS? It's RMS. When I say your house is 120 volts right there, that is RMS. What is RMS? Well, RMS is the same amount of AC where I get exactly the same work as AC into a resistive load. So if I was to come over here and put a 1K resistor in that thing, it would give me exactly the same work if I put that on 120 volts DC. And we're calculating VP. Peak will always be more than RMS. It's like the peak of a mountain will always be higher than the average, right? Understand that? 0.8. Anybody else got that? Now I'm going to put VP. I'm putting VP because now it's not RMS, right? You understand that? So VP out is going to be equal to 17.8 minus 0.7. Why? Because we're dealing with a silicon diode. Is it exactly 0.7? No. But it's close enough to know that we're going to get a pretty good answer, right? You understand that? So what would VP out mean? And we're going to subscribe this to make sure we understand, right? Okay, so what would the DC averages be? So I take 17.1, so volts DC. This is what my meter is going to measure. It's going to be 17.1 divided by 1.3, 3.14. What should we measure with our meter? And how much work should a light bulb do? How much work could a motor do? So light bulb, it don't care about pulsating DC, right? You understand? It's nothing but a resistor, right? A motor don't care about pulsating DC. It'll run just fine. If I was, what's that? I'm using volts, DC, half wave.
Okay, back to half wave.
No, full wave. I can't do full wave with one diode. Because somehow I've got to get the other alternation, right? You understand? So we're still on halfway. Guys, I'm sorry.
Because I thought that combined 6.3 together, 6.3 would be half, 6.3
No. We're just doubling the output's going to double because we're doubling the input voltage. When we go to halfway, we're going to get double what we got for DC for that amount of AC, right? That makes sense. I've got to have at least two diodes to get full wave because somehow I've got to get the positive. So this is half wave right here. This is full wave right here. So when we're talking about full wave, I get the entire both alternations. It's just somehow I'm going to take the negative alternation and the positive power supply. Somehow I'm going to take the negative alternation and pop it up on top too. You got to have at least two diodes. That makes sense now? Just because we double the input voltage, it doesn't mean that we're full wave, even though the output's going to double. Why is the output going to double? Well, we double the input. So when we talk about full wave, we're going to get double the DC for the same amount of input. So sorry about that. So what should I expect to measure with my meter? And this is volts DC. So 5 volt power supply will work great with this. Anything that needs 5 volts, if it's not electronic, right? Are we okay? Anybody didn't get that? So I'm gonna take my transformer and I'm gonna go all the way across the outside. Okay. And then I'm gonna come over here and take my meter and I'm gonna measure across the load. I point one volt. Which I'll calculate. So a 5 volt light bulb would work great off this, a 5 volt motor would work great off of this. I don't know what this guy's rated at. Just don't have any specs on it. This transformer should be able to handle this. Which I can't see, I need a piece of tape on it. But it's running fine. But DC motors don't care if it's half wave or full wave, they don't care. Just if it's full wave, the motor will run probably twice as fast. Right? What happens if I put a DC motor across the AC? Well, with a transformer. Huh? No, I just try to keep reversing direction. They just sit there and run it. That was good. That come up for off the full motor. The DC motor running off the DC power supply. Okay? Yes, sir. 5 volts. So this looks like it might be a 12 volt motor. I'll run it real fast. Okay, 1K resistor. How much work am I getting out of my 1K resistor? How much work am I getting out of my 1K resistor? Work is not rated in 12.6. What's work rated in? What? No, we're using DC. We're using this voltage right here. This is the DC. This is the DC we're using right there. 12.6, right? You understand? We're gonna get the work. And this is. So how many watts are we getting out of my resistor? I don't want to burn my wick resistor up. Everybody's in here has DC, right? What's your formula for power? Yeah, but there's one a little easier to use here. I square R, but then we have to calculate I again. So V squared over R would be the one I would use, right?
So 5.4 squared over 1,000, that's how much work we get out of it. Or you can, huh? 1K. Brown, black, red. You can use I squared R, you can use V times I, but what's nice about this, we know the voltage and we know the resistance, so we don't have to calculate the current. What's that? Which is what, we're using a quarter watt resistor, which is 250 milliwatts, so we're fine. So that resistor's not even getting. So okay. Yes, no.
Brown process.
Process. Okay, guys, y'all go ahead and take a 10-minute break. So 100 volt peak, so we're giving you the peak value. And we're going to use the silicon diode. Of course, here, guys, it's not going to make much difference because it's 100 volt peak, right? We're working on this right now, guys. So if I was to come over here and give the whole sine wave, let's see if we can find one that's got the whole sine wave where we can actually. In fact, it would probably be better to do RMS because RMS is what you're going to measure with your meter, right? You understand? So RMS is what we measure with a meter. So let's say that's the AC.
Yeah.
And your meter is measuring it's measuring RMS. So our meter is basically taking VP. So the meter, if it's not a true RMS meter, is doing this formula inside. Taking RMS. What the meter is doing points out. That's what a standard meter is. Right, you understand that? So this is, and what is RMS? That's what it stands for, but what is it? Well,
So this right here would do exactly the same work into that 1K position. So 12 volts RMS would create the same heat and do exactly the same work as 12 volts DC. And that's what RMS is. So over here, if I was going to calculate how hot this resistor would be, then I'd use 12 squared over 1K. Over here, I would use what? I'd use 12 squared over 1K. That's because that's what RMS is. It's actually what we're getting work out of. And it's not, it can't be an average because what's the average of this? What would be the average voltage? The average voltage would be 0. We proved that. I can take this meter right here, I can put it on DC, and I can put it across that transformer, it's going to measure 0. Because what your DC does is it gives you the average, right? It gives you the DC average of a cycle. What's the DC average of a cycle? 0. So they had to come up with a method where we can do away with the minuses, right? You understand? So if we square a minus number, it becomes a positive. So that means, okay, if I square all these numbers around that sine wave, I'm going to come up with a positive number, right? You understand? And then I add them together, then what I'm going to do is I'm going to come up with an average, which is, we call it a mean, but now it's a lot higher than it's one. So we squared them to start off with, so what are we going to do at the very end? We're going to take the square root, and that's the way that's the way these meters work. But if it's a sine wave, if it is a sine wave, it always comes up to be 0.707 or 70.7% of VP, or the sine of 45 degrees. Every one of them is exactly the same. Okay. So that's where the 0.707 went. So yeah, you could do it this way. You can come up here and calculate it. You can take a bunch of these and square them. You can come over here and square them, right? You understand? But then add them all together, and then take the average of that and take the square root. Now, this is the way meters have worked for years. But now, when they came up with this thing called a microprocessor, it means that sucker can do math. So we have meters that actually do true RMS. If you took this meter here and this meter that costs twice as much, and all you do is electrical work, and all you deal with is sine wave, you wasted a ton of money on your true RMS meter. These two meters are going to measure basically the same. The only time you need a true RMS meter if you deal with AC waveforms that are non-sinusoidal. That means they might come up and look like this, where this is okay, and then this right here might look like that. Now this meter, if that uses 0.707, it's not going to calculate it right because that is not a sine wave, right? It's still AC. So if you're dealing with devices like variable speed AC drives and stuff like that, and you want to see the average AC, then you're going to need a true RMS. If you're just dealing here, you don't need a true RMS meter, right? Does that make sense? Because you're going to pay about twice as much that you would a regular meter. So this is where the 0.707 comes in. So this is what just about every meter you got in here. That's like having a car that'll do 300 miles an hour. Yeah. You'll have nowhere around here to drive it, right? Yeah, we had a guy. He was in a big old nice brand new pickup truck. He was in a 45 mile an hour speed limit yesterday. He was doing about 70. Come around me like he was sitting still. Guess who whipped in right behind me? Yeah,
The bad one over here.
huh?
The bad one.
What, this one? Where they give you all the averages? This one? This one, this one, this one, this one, this one, this one. I think it's the one where it gives where it actually.
The one after that.
This one. This one.
Still on the database.
By the way, some books say that V average is equal to VP out times 0.318. Where did they get 0.318 at? Yeah, well, all they did was they did this, they went ahead and did the math for you, right? Y'all understand that? They took the reciprocal of pi. What's the reciprocal of pi? 0.318, and that's, so you can, some books teach that, but they don't. Is this the one you're talking about right here?
No, I already got it.
So what would this average out? What would the average be out here? No, the actual DC average output. Right here. This is DC. If I put my DC meter right there, it's going to measure 0. This gets people confused too. If I put it over here, it's going to measure something because now it's what? It's DC. Over here it's AC. Now what would the DC output be? What would I measure here? So if I had my meter set on DC right here, over here it measures 0. If I take my same meter and put it over here, and I have it set to DC, it's going to measure, what'd you say, Bernard? Or about 1.6 volts. Now why does it measure 0 over here and it measures 1.6 volts over here? Well, over here it's going to be the average of a sine wave. Over here this is DC. It's going to measure the DC work that I'm going to get out of it. So I got 1.6 volts over here somewhere. Anybody else got anything different?
I don't understand what you're just.
Makes sense. So what I'm going to do is, here's my circuit. I got my meter on DC. I got my meter on DC. I'm going to measure across the transformer. So this is my input. And it shows 0 volts, right? Let's do that. I'm going to come across the load, and it measures. I got to turn the train on. Let's go back and redo that. Train on. Yeah, I don't think. So here's measuring what? This is across the transformer. Pretty close to 0. It's 6 millivolts. This is across the load. So I got 5.1 volts here, and I've got 0 volts here. Now if I put my meter on RMS, now it should measure about 12.6 volts. And that's why our calculations are a little low, because it's not 12.2, 12.1, right? It's the 12.6 was given us to calculate. So this is what we're talking about. So, and this gets people hurt, right? You understand why? Because what they'll do, they don't think about what their meter's on, and they'll come up here and do what? Yeah, they'll come across here and they're measuring an AC source, and what does it show? It's going to show 0, right? You understand? Six millivolts, that's pretty close to 0. I get that from here, right? Well, AC induces voltages in everything. So I measure more up here than I am what in the circuit. It's almost hard to make an AC meter measure 0 on a small scale like this. So this is why it's important for you to know that if you're in the AC circuit, double check your meter to make sure it's what on AC. Like some of these meters use the same scale. This one don't. Luckily, this one don't use the same scale.
Well, we have some meters that use exactly the same scale, and you gotta remember to push a button. I'm trying to figure out where my other meter is. Here, that's the meter here. And it's got one scale for both. You gotta remember to push a button. So that makes sense, Brian? So everybody got 1.6 volts? So this is V peak over here, V peak. So over here we're dealing with it. So this is V peak. Here it'd be 5 volts. There it'd be over here it'd be 4.3. Right? Because we're on this now we're on this side. And then we'll come up here and divide that by 3.14. And this should give me volts DC. We okay? One thing we gotta understand, and we'll look at data sheets on the book on later. But a diode can only block so much voltage when it's reverse bias. Most books teach this as PIV. I think this book actually teaches that PIV. But when you actually look at the data, I gotta get that off there. Whoever uses computer last. So I think I'm using a 4000 series. This should be up on Blackboard, but so this covers a 4000 series, so it covers all the diodes between a 4001 and a 4007. And this peak reverse working voltage, this is the guy we're interested in. So a 4001 could block up to 50 volts when it's reverse bias. A 02 could block up to 100 volts. An 03 could drop up to 200 volts. So this is one of those, if you're replacing a diode, you might not be able to get the same diode that you have, right? You understand? So what you're looking for is you're going to look for one that can handle the current. So how much current can this guy here handle? No, you can't see it. Current, Brian. There's a dot right there. Yeah, so these are 1 amp diodes, and it's all the way across the whole thing. So it's saying, okay, every one of these could handle 1 amp. But a 4001 could not block as much voltage as a 4007, right? You understand? So a 4007 could block up to 1200 volts. A 4001 could block up to 50 volts. This guy here says it could take 30 amps for 1 cycle. So unfortunately, books teach PIV for peak inverse voltage, but just about all your data sheets will call this the reverse working voltage, right? VRR. So that means that's something I should have checked before I put this diode in here. I should have made sure that it had the ability to block that negative alternation, right? You understand that? So I think this book teaches PIV, but like I said, it's not going to be that in data sheets. And we're talking about this. We're not talking about DC average. We're talking about this peak down here. So that's another reason you need to be able to solve for V peak, right? Because that's what the diode is going to have to block, right? If you buy a transformer, what voltage is this transformer going to be rated? Peak, peak to peak, or RMS?
No, it's RMS.
RMS, right? So this is a 12.6 volt transformer. So they're rated in RMS. Why RMS? Because that's how much work they'll do into a resistive load, right? You understand? But what I have to do is I have to figure out what the peak in voltage would be out of that transformer, because that's what's going to bop my diode, right? Does that make sense? And how do we solve for peak if we know RMS? Yeah, the RMS right about 0.7. And you need to make normally we shoot for twice, so we usually double this on our diodes. So I think I got a 4001 right here, which would be right. So this is DC. What would my average DC output be? What is the DC voltage? So we don't have to take off the 7/10 because this is the DC, right? Did we do this one already? I think we did 100 volts. This is going to be 1/10 of that last answer. So what would my DC average be? 3.18. Everybody okay? Everybody okay on the negative? So what we're doing, how do I know this is a negative power supply? To the source, right? Yeah. So here our source is going to be so we know this is going to be a negative power supply. So we know we'll be getting this out. Right? Everybody okay there? Yes, no. DC average, we would calculate it exactly the same, except we're going to have to remember to put the minus sign out on our voltages, right? Everybody okay? Huh? Just put the negative on. Yeah, you calculated exactly the same. Just remember to do what? Put the negative sign on your answer. Full wave. So somehow we're going to have to take the negative alternation and do what? Put it up top, right? Or vice versa. It depends on whether it's a negative power supply. So what we're trying to do is we're trying to end up, instead of ending up with this, we're going to try to end up with this, right? Everybody understand? We got two full wave rectifiers. So this will be our formula now. VP, 2V peak over pi, right? 2V peak over pi. Everybody okay? Or if you want to remember the fraction, you can use 0.637. So this is a full wave rectifier. Now what advantage is a full wave rectifier? Well, we're going to have to add more diodes, but we're going to be able to get more voltage out of it, right? You understand? The higher the voltage, the less of the current that's required to do that work. The first we're going to do is look at one that's, so what would this be? Well, this is going to be 2 VT over 3.14. So now we can use the 2 because we don't have what right here? We don't have the 0 that we're averaging in there. So this would be 15 volts, right? Divided by 3.14. And what would my volts DC measure? Oh yeah, thank you. I was just making sure y'all was paying attention. I'm still back on halfway. So what should we expect out of this guy? 9.5. Yeah, because the 0 is not in there, right? So the way we came up with this guy, the average for an alternation is over 5. So when I come up here and do this, what are we averaging that with that? We're averaging it with 0, right? Over here, this is over pi. This is peak over pi. This is 2V peak over pi. So if I added all of them together, I would come up and get 2V peak over pi, right? You understand? So with full wave, we get the 2 V peak over pi. With half wave, all we get is V peak over pi. So first one we're going to look at is it's going to require a center cap transformer. Of course, we know transformers. What do transformers do? Power does not what? Okay. What determines how much power is whatever load we hook up to this thing, right? Now this is ideal, but we're dealing with only one little transformer. So like Alabama Power or TVA would really be concerned with the efficiency of the transformer because they're trying to get power over a long distance. Normally when we get to our transformer, we assume they're 100% efficient because they're over 95% efficient too, right? You understand that? So this is a full wave center tap. And what we're doing now is we're establishing a ground or we're establishing a common. Everybody okay? So what's going to happen? Well, you know when this side of the transformer is plus, this side way down here is going to be what? Yeah. Well, this would be negative in respect to that, and this would be positive in respect to this. Do y'all understand that? Okay. So what happens if this is a 12.6 volt transformer? This guy right here's got 6.3 volts. So it's like a resistor. If I have plus 6.3 volts there, what would I have right here? Well, it's going to be minus I would have 0 in respect to that, right? Does that make sense? Now, if I come down through here, this guy's got 6.3 volts. Here's my minus, so this has to be plus in respect to this, and then this has to be minus in respect to that. Let me do a different color since the black is blending in. So if this right here is plus, then this right here has to be minus in respect to this, right? Y'all understand? Yes or no? And if this is plus, this is going to be minus in respect to that. Yeah. So right now, what I would have, if I follow this over, this right here would be a minus. I'd follow over, that right there would be a plus, right? Everybody okay? So this guy right here is definitely going to be, is it going to be on or is it going to be off? Relative to 0 volts. Okay, to forward bias the diode, I have to make the anode positive with respect to the cathode. This guy is pointing towards 0 volts. This guy is pointing towards minus. So over here, what we have is this guy right here has to be off, right? That makes sense. Yes or no? Yes or no? Okay, now this guy has a chance of being on, so this guy right here would be what? On, because it's got a positive on the anode. This guy here's got a negative on the anode. This has got a positive on the anode. So this diode's going to turn on. So where's its negative at? Its negative is right here. So what's going to happen? Let me change colors. This current's going to flow out this, right? Through ground, through common. It's going to come back up here. That's going to make the bottom of the, and what's it looking for? It's looking for its diode. So which way is it going to go? Is it going to go up or is it going to go down? This guy is on. It's acting like a closed switch. This guy is off. It's acting like an open switch. Which way is it going? Huh? Current doesn't flow to an open, right? So it's going to go through the diode that's on. It's looking for its positive. So if this is negative and this is positive, it's looking for its positive. So it would go back
through the diode, it is turned on. So it means the bottom of the current flows, this is negative, this is positive, so this would create this, right? Then on the next alternation, then everything's going to swap, right? So if everything swaps, dang it. If everything swaps, then now this is negative and this is positive. Right? That makes sense. Okay. So what's going to happen up there? Here's negative on the anode. What's this guy going to do? It's going to turn off. Here's positive on this anode. This guy right here is going to do what? It's going to turn on. So current's going to leave here, right? This, okay. Come through here. It's going to go up through the diode and the resistor in the same direction. Okay. It's going to come over here. And which way is it going to go? Down and back through this. And what this is going to do is it's going to do this again. And then the next alternation, they're going to swap, and it would do what? It would do this. Everybody understand this? Yes or no?
No, I don't completely understand.
So let's start off again. So when this is positive, what's this side of the transformer? It's got a negative. Okay, so that puts a positive right there, that puts a negative right there. Which transistor is going to be on, which diode is going to be on, and which diode is going to be off? Okay, this guy's going to be on, so it's acting like a closed switch, right? This guy right here is going to be what? So there's no current can flow through the bottom.
So how I know that bottom?
Because of this guy right here. I got a negative on the anode, right? You understand? Here I have a positive on the anode. Okay. Relative to this side over here. Well, what's this side over here pointing to? It's pointing toward what we consider to be 0 volts. So this guy's pointing towards 0 volts. It's not going to be there. So 0, because we have the resistor, right? You understand? So it's not going to be 0. It's going to be 0.7 of a volt less than what this is. But this guy is pointing toward negative. This guy right here this guy's pointing toward negative. So this guy's pointing toward negative. This guy right here is pointing toward negative. So here I've got negative, negative. This guy don't have a chance of being on, right? You understand that? Relative to 0 volts. So if this is positive, if this is 6.3 volts, then this is 0 relative to that, right? You understand that? Okay. So here's 0, so current's going to flow down. This is 0 volts. It's not no volts, it's 0 volts. So current's going to flow out this. It's going to come up through here. And which way is it going? Can't go this one because this guy's what? Off. It's acting like an open switch. So if I came up here and drew this like this as a switch, you say, well, current can't flow through an open switch, right? If I came over and drew this one like that, you say, okay, that's the way it's going, right? You understand? Oh, you like my... So which way is it going to go? Is it going to go through the closed switch or is it going to go through the open switch? Huh? Which way is it going to go? Closed switch. So it would flow up, all right?
Oh, so they ground over here on the right, the ground all over here, far right, and then the ground inside the transformer.
It's not inside the transformer, it's out. It's me. Transformers don't have grounds. That's one thing you got to understand. Right off the bat, we use a lot of symbols. So I could come over here and I could have a very complicated circuit. Let me find a slide. Open the slide. I'm going the wrong way with it. So what I'm doing is I'm using a symbol to represent a wire. So instead of drawing inside that meter, we got a comma. And all this stuff is going to it. Well, what happens is the more wires you draw, so what you have to know in your mind, there is a wire there. It's just that I'm replacing that wire with a what? With a symbol. With a symbol. So every circuit's got to have common. So that would be the obvious one to replace with a symbol. And we have that all the time. People will see that and they think it's, so they'll come over here and hook up this circuit right here.
I know, I just didn't know it was that same illustration. It was the same illustration for the stretch that.
So what we would do, if you wanted to see this, the way the circuit is actually wired is a wire that is running from here. As soon as I get the right one, got the razor. There's a little wire running from here over to here. So this symbol is doing what for us? It's replacing the wire. So the less wires I have in a diagram, the cleaner it is, right? You understand that? So that's what they've done. Every circuit's got a common. So they came up with a symbol that replaces the wire. Is the wire, do I have to hook that wire up? Yeah, you got to hook that wire. You got to know that it's replacing a wire, right? So what I know is since this is hooked to common, that the current flow is always going to come out the common, right? Because that's, in this situation, it's the negative, right? Y'all understand what I'm saying so far? So I know the current is going to flow out of this, since this would always be negative in respect to what it's measuring. Then current's always going to flow out this one, but it's going to do what? It's going to flow up there. Since this is considered the negative, the bottom of that resistor will always be negative, and the top of it will always be what? Positive. So it means if I come over here and make this positive, then this guy right here has got to be less positive, because it's on the other side of a. So if I came over here and I put a resistor, and I said I had 10 volts right there, you know that right there has got to be what? Is it going to be 10 volts? It's going to be what? If I put this across the DC source. Is it going to be more than 10 volts or is it going to be less than 10 volts? Okay. So that means if I was to come over here and take my meter and put it across here, it might be dropping 5 volts. It's going to show a positive 5 volts. Right? You understand? Now, if I was to take that same meter, so if I was to take my meter and put it here, I put my black lead there, my red lead there, it'd show plus 5 volts. Well, what if I just left my common right there and put it right down there? What would it measure? Gosh, no. So what I'm doing is I'm taking, you're right, it's going to be 5 volts, but it's going to be negative 5 volts, and this is what we're doing here. So if I was to come over here and call this my common, okay, and this was 1K and this was 1K, if this guy here would drop 5 volts, if this is 2 volts, this guy here would drop 5 volts. I'm always going to leave my black lead on my meter right there. I come over here, this guy here would measure plus 5 volts. I come over here and go down to there, that would measure minus 5 volts. So that's what we're doing here. So here's my common. So that means if this was plus, right, you understand, this would be minus, right, you understand what I'm doing. Well, this would measure minus, this would measure plus, relative to what? If I could see it at any one instant. So if this is plus, this would measure what? This would measure minus, so that's going to put a true minus right there. This would measure plus, so that would put a true plus right there. Right? You understand? So what we're doing is we're doing this right here. And what we're doing is we're just making, instead of making the common on the bottom, we're making the common in the center. Y'all understand that? So y'all understand why this would measure minus. So we're doing exactly the same thing, but we're doing it with a,
because our common is not right here. Now, if my common was down here, if my common is right here, I would measure 5 plus 5 volts right there. But look where our common's at. Our common's not right there. Our common is where? So that means my meter will measure plus on the top and it would measure minus on the bottom. So that's why I'm putting the plus right there and the minus right there, right? Y'all understand that? Because where we reference them from here. So if this is the minus, if this is the common, then it was going to flow out, it's going to come up through here, so that would make the top of the resistor positive and the bottom of the resistor negative. And if I came over here on my next alternation, then what's going to happen? This is going to go minus, this right here is going to be plus. Right? So now what's happened is as I swap my power supply around, so my DC is swapped around. So that means this guy here now would not, this right here would be what? This right here would measure minus. So that's what you got to understand is we're taking the same basic circuit over here, but what are we constantly doing with the DC source? We're swapping it back and forth. So if I come over here and I make this minus, and I come over here and make this plus, then this guy right here is going to turn what? On. This guy right here is going to do what? Turn off. Current is still going to flow out this lead, and it's still going to flow up through here. But here, which way is the diode is the current going to go to now? It's going to look for its positive, so it's going to go back this direction right there. So what's happening is we're using two diodes in a center tap transformer. We're automatically making the current through the resistor go the same both times. So it's not swapping. So if I look at this with an oscilloscope, what I'm going to get now is I'm going to get this, which is full wave. But I'm only using 1/2 of the transformer. So if this is a 12.6 volt transformer, which is the way this thing over here should be written. So when we give the size of a center tap transformer, we give this right here, 12.6 volts, and we would say CT for center tap transformer. How much am I actually using at one time? Am I using both sides of the transformer at one time? So if this is 12.6, what would I get on my output? So if this is a 12.6 volt center tap transformer, what DC should I expect to measure across that resistor? You forgot all about that V peak over 2V peak over pi. You're trying to go directly. You're trying to give me this instead of trying to get me what this DC would measure. 4 volts? How'd you get that? So we're just forgetting everything we learned. We're jumping directly from RMS over to VP without going to VP. So that 12.6 volts is RMS. My formula says 2, it don't say RMS. It says now my volts DC is going to be equal to V peak out, not RMS, over 2V peak out over pi. So y'all are trying to go from RMS directly to the output without finding what V peak is going to be. So what I'm going to do first of all is I'm going to calculate V peak. Okay. So we're only using 1/2 of the transformer, so V peak secondary is going to be 6.3 divided by 0.707. Anybody do that? Why are we using 6.3 instead of 12.6? Because we're only using 1/2 of the transformer at any one time. Which is because we could actually get twice the current out of 8.9. Okay, so that's 8.9. Are we okay so far? Now this is voltage peak.
Then I'm gonna calculate V peak out. This is gonna be equal to 8.9 minus 0.7. 8.2. Then I'm gonna calculate my DC, my volts DC would be equal to 2 times 8.2 divided by 3.14.
What we got?
5.22. 5.2 volts. And this is DC, right? Well, what you got to understand is that when this is positive, this is negative. Okay. All right. So what would happen? This transistor, this guy here would turn on. Which would my current flow though? It's going to come out of here. So which side of the transformer is it coming out of? At the top. Okay. So if this is 12.6, if it's coming out at the top, all I see is what? 6.3. So, but when you buy the center tap transformer, it don't come, you don't say it. You don't buy it as a 6.3 center tap. You buy it as a 12.6. That's the way, that's what I don't like about the trainer, because they show you the 6.3, but if you took the transformer out, it's going to say it's going to take a 12.6 center tap. And I go try to find one of these transformers for you. So it's rated at the full voltage. It's not rated, but we're only using 1/2 of that at any one time, right? Does that make sense? Right?
I guess it's going to run off the
It is. I understand this. So what we're looking for these formulas that says DC, and I think it says full wave CT. Is there any formulas like that on there? It might not be CT. It might just be full wave. Yeah, so VP, V secondary, so this is my secondary voltage, divided by 2, which would give us what? 6.3. Y'all see the formula on there? Yes, no. What formula number is that? 13. $12.6. Yeah, it covers up. I'm sorry, guys. So we buy a transformer. So if I was going to buy a transformer, if I looked them up, they would call this a 12.6 volt center tap transformer. And of course, is that 12.6 is going to be RMS, right? You understand that? Okay. But on a full wave center tap, we're only using one at a time. So I think the formula says what? Yeah, V peak secondary divided by 2. Minus the forward voltage drop. Yeah. So y'all see how that's why we're divided by 2 now, because we're only using one side of the transformer at any one time, which is pretty neat, because I could get a 1 amp transformer and I could actually get 2 amps of work out of it, because what happens is that the transformer's got a half a cycle to cool off, right? You understand that? A lot of people don't know that too.
So let me go up here, let's hook this up. Okay, so here's my transformer. Okay, turn my trainer off. There's my load. So I'm gonna make a full wave bridge. So notice what happens is that, go back to our diagram. So notice, are these in parallel?
Yep.
No. Why?
They all in series. I thought you meant parallel, like,
Yeah, so parallel would be this. So parallel means I would have a would have to be connected together. Here the cathodes are connected together, but the anodes are not. So this is not parallel. So what I'm going to do is I'm going to come up here on my trainer and I'm going to connect the cathodes together. So we'll make a positive supply. So here's one of my diodes. What did I do in my other one?
Flame up there, Rick.
Dang it. I'm going to take my common and I'm going to hook it up to the bottom of the resistor. Right? So this is the actual schematic. And this is the way I have it hooked up. I have my cathodes connected together. I got one of my anodes going back to one side of my transformer. I got my other going to the other side of my transformer. And then I've established this common right here that goes to the bottom of the resistor. Now remember, this is a symbol that represents a wire. I mean, I've heard it more than once. I thought that was inside the trainer. It's not. This represents a wire. This represents a wire, right? So here's my circuit. Everybody okay there? I'm going to take my oscilloscope now, hook it to common, hook it across my resistor, get the end of my finger. Both ends, not only if I want to short circuit. Okay, so this red wire here is my common, and it's replacing that. So all we're doing is replacing this wire right here. Right? You understand? Yeah, if I put a common on both sides, then I would have a short circuit, right? So this is connected to one side of the transformer. And it's going up to one of the anodes of the diode. This is on the other side of the transformer. It's going up to the other anode. I have the two cathodes connected together, right, in the same vertical line. And then this would be what we call the common for the circuit. The common means we're going to make our measurements relative to that, right? I'm going to come up here, take ground on my scope and make sure I hook it up to the common. And what I'm going to do now is hook it up across the load. means I can hook this up to any of this common line. The diodes are a little easier to do because they have a bigger lead on them and they want to stay in. The resistors have a real small lead on it. So if you hit your scope probe, it'll pull it right out of the plane. And of course, we should notice a big difference. Now we have full wave, right? Here's my zero. I shifted my zero down here. So this is 0 volts. Looks like we might not be triggered. Can y'all see it moving? Just get that line within the waveform. And now it's away. Now this is a cycle. So what I've done is I've literally taken the AC I can only look at one side. But what I've done is I've literally taken the AC and flipped the negative alternation up to the top, right? You understand that? So that means this guy right here, the frequency now of my pulses are now, instead of being 60 pulses per second, I'm getting 120 cycles per second. So what is a cycle? It's the number of repetitions per second. So here, this might be the positive alternation, this might be the negative alternation, so I'm getting 2 cycles for every one AC input cycle. So instead of this cycle being, so this would be 1 cycle right here, so that'd be 8.33 milliseconds, would be 120 cycles per second. Put 60 cycles in. And this is full wave. So what happens is we get the twice the voltage for the same input, right? You understand that? Plus now on a half wave, one of my diodes is only on at a time. So that means I could use 1 amp diodes to run a 2 amp load, right? You understand why? Because when one diode is on, the other one is what? Off. So we could use 1 amp diodes for a 2 amp load. The biggest disadvantage to this is we're having to use a center tap transformer. So a center tap transformer costs a lot more than an untapped transformer, and of course, and we're using more diodes. So this would be more expensive, but we get more out of it, right? That makes sense. So what did we calculate we should measure when I measured this with my meter? Anybody still got it? Five point two. We got 4.8, 4.9, so that's 300 millivolts different. Now, why are we measuring something different? We're measuring, and our transformer is not 12.6 volts. We measured that a while ago. Our yeah, we're doing it. Yeah, exactly right. So the transformer is actually so instead of being 6.3, it's actually 6.1. But we're close enough to just use what the transformer says it is, right? You understand that in our calculations, and then we understand that instead of measuring and then calculating, we're just going to use what we think we get out of it, or specify
that. He's still worried about it.
Yeah, what we're going to have to do, guys, we've lost it. We lost almost the whole day because we had the power out. We'll probably move our test to next Thursday because we got one more. We got one more to go. We got to do. We'll come back and touch on this. We're going to do a full wave bridge in class. Then we're going to go to lab where we'll be in lab. So make sure you bring your lab book and your meter next class. Right, we're going to be in lab. I'll give you a worksheet on power supplies. You'll do that during the weekend. We'll turn that in, on next Tuesday, right? And then so what I'm gonna do is I'm gonna move the test to next Thursday. Is that okay with y'all? We got one quiz. We've only got one quiz that's due.
It's two on chapter one.
Yeah, two for chapter one. One of them symbols.
You got one quiz due this Thursday. You got two quizzes. Two.
Okay? So if you got your book, look over full wave, look over full wave bridge rectifiers. That's what we'll be talking about next. And then we'll go into lab. So make sure you bring your what next class? Make sure you bring your safety glasses. We're gonna wear safety glasses in this class, right? You understand why? Because diodes, if you put them there wrong, they will pop on. Solid state devices, they don't just burn up like resistors do, they will pop on. I'll show y'all the, huh? Go ahead, I know you're.